Good morning. Welcome to Krishna's classroom. Let us continue with the abstract integration theory. Our objective is, of course, doing the Riesz representation theorem, which is one of the central results that connects a linear function with a measure. We have seen the statement of that in the last lecture. Then we said that more than the algebraic structures of the space X, in fact, you don't put any algebraic structure on the space. What is significant is the topological structure that is there on the space. I mean, it's not that to define a measure space, one does not require any topology on the space. That's something. And in fact, there are situations where you come across the non-necessity of a topology on the space. But generally, for doing analysis, we require, or it is quite significant if you have a topology on the space. So what you have is a measure space X where we take the sigma algebra to contain all open sets X. Of course, we are assuming X tau topology. In fact, we take the smallest complete measure that contains tau. So this is what you have. Tau is, or the collection tau, that is the open sets on X are all measurable sets. Therefore, this is contained in M. And we take the minimum that is required is a sigma algebra M, which contains all the open sets, and we choose the smallest complete sigma algebra or complete measure space, which contains where all open sets are measurable. Now this facilitates, we have already discussed this, all continuous functions real or complex value on X to be measurable. That is, all significant functions, or there is a huge class of measurable functions defined on the space X, and it contains all the continuous functions. Therefore, you have a nice a broad collection of measurable functions to work with. Because you know that for integration theory, we would like all continuous functions to be measurable so that an integral can be found. We call whatever we did for Riemann integral and Lebesgue integral. Both the situation is there. In fact, I have said here real or complex value. This need not be. In fact, it can be something like this. X is a topological space. Y is another topological space. And you are talking about maps from X to Y. Y is topological. That's the assumption that we are. Now we would like for all open sets here. Okay. So you take A open in Y, then we look at this one. F inverse of A is an open set in X whenever F is continuous. Therefore, you see that all continuous functions from X to Y are measurable provided the sigma algebra that you have set up on X contains all continuous functions, so that you are assured that F inverse of A is an open set in X whenever F is continuous. I mean that is the definition of continuity, and F inverse of A is to assure this. What we are doing is that M contains all open sets on X. So that is the explanation. So we take this scenario and work on that. And often these topological properties of X do contribute to the integration theory, as we shall see later. But we shall do some preparatory work, and this is what we have defined several concepts of topological concepts, and now we are in a position to take up some of the results on compactness. We have defined compactness and local compactness. Compactness is a property of a set of the topological space. We say that suppose K is contained in X is compact if every open cover for K has a finite subcover. This means if V alpha is open, if V alpha is some index set and K is contained in V alpha, so that it becomes an open cover for K, then there exists finitely many A alphas such that K is contained in K is contained in N 1 to K. So not all this, the entire collection of open sets is required to give a covering. For any open cover that you choose, there is a finite subcover. Now, for example, on R, all closed bounded are compact. And in fact, this is a characterization of compact sets. Now you see that the same characterization works on Rn. The same characterization of compactness works on Rn. Works on Rn. That means a subset of Rn is compact if and only if is closed and compact. This is the famous Heisenberg theorem. That is, every a subset of Rn is compact if and only it is closed and now one could ask the following question: is this characterization universally true? That means you are given a arbitrary set X with a topology defined on it so that it becomes a topological space. Can you say that compactness in X if and only if the set is closed and bounded? But this is not true. This result is not true in general. In Rn, it is true, but not in general. For instance, if you take the L2 space, which I have explained last time, in L2, the unit bond, closed unit bond, its center at 0. This is bounded but not compact. So on a general topological space, one cannot make this statement, but on certain very useful topological spaces like Rn, it's a nice characterization theorem which is available for us. So that's about recalling what compactness is. Now we say that you see that if you take a space which is compact, okay, then you will see which subsets are compact. That we will discuss soon. Okay, but like R is not a bounded space. Nevertheless, there are a huge class of subsets which is compact, namely all closed subsets of R which is bounded is compact, and that is stretched towards R. Okay, but we have seen that is in general this is not a characterization. Right. Now this is the famous Heidelberg. Very useful when you work on topological spaces. Now you see that we can define the space may not be compact, but it may be locally compact. So what do we mean by this locally compact? X at tau is said to be compact if every x belonging to x has a neighborhood whose closure is compact. That is what we mean by a neighborhood. A neighborhood is an open subset of x which contains x. So if every point x has a neighborhood whose closure is compact, then we say that the space is locally compact. Now Rn although not now all compact sets, all compact locally compact. Now that's another result. However, there exists topological spaces which are not locally. For example, L2 which usual topology. Not locally compact. Because you see that in L2 we have already said that unit ball, the closure of the unit ball is not compact. Okay, so you take any point x belonging to L2, choose an open neighborhood of that. It could be something of the form of an open ball containing that point. You take the closure of it. Okay. Therefore, you see that the space is not locally compact. So, not all spaces are locally compact, but there are several spaces that are locally. So, let us keep all these definitions in mind and then go further. So, yet another property that we need is a separation property, which is called Hausdorff property. X tau is a Hausdorff space. It's a Hausdorff space. If given 2 points in the space, they can be separated by open sets. It's not equal, right? There exists open sets U and V such that X belongs to U, Y belongs to V, and U intersection V. That means they can be separated using open sets. Now, this nice separation property is also relevant in the context of our studies. Okay, so that is the Hausdorff. Now, there are several examples for spaces which are not Hausdorff. For instance, if you take X with the trivial topology, and X has more than one element. So, if you take two elements X and Y, now you see that you cannot find two open sets U and V such that X belongs to U, Y belongs to V, and X intersection. What is that? U intersection V is because the only open set that contains X, that contains Y, is capital X. Okay? So you cannot separate. So that's a trivial case. There are many examples. But what we are interested in, spaces which have this nice property of Hausdorff separation. Now, one of the immediate results that you have you have is that every metric space a Hausdorff. Now let us prove the following theorems. The first theorem that we look at is this. Every closed subset of a compact space is compact. This is a nice property. If you have a compact set, then take closed subset of that and it becomes a compact. So let's give a proof of this. Set of X. So we assume F is closed. F is closed. Now we claim so we have to show that if every open cover finite subset. So let us work on this. So F is closed let W be equal to F complement. Then this is open. This is open. So we have union alpha. Suppose V alpha is an open cover. Then X is and take it. Okay. So be an open cover. Then B alpha comma W is an open cover. An open cover for X. Now X being compact, what is it? That is, there exists V1, Vk, W, a open cover for X. Because X being compact, just finite subset. So we can take out V1, V2, Vk, finitely many of them, such that this union W is the open cover for. Now X is compact. Okay. That's how we have a finite. Now clearly you see that V1, V2, Vk is a cover for now you remember if F is closed, we have used the fact that F is closed. It's from the fact that F is closed that we have F complement is open. F complement is what we call W. Now what you do is you have a finite subcover for the whole of X, and from that you just remove W. then what is left would be a finite subtower or the cell. So every closed subset of a compact space concept. So we give a corollary. If A is contained in, we are working in the context of a topological space, and if B has a shift, then A has a complex. What is the closure of A? Closure of A is the smallest open set, the smallest closed set that contains A closure is that's the definition. So you have A is contained in A closure, that is true. So A contained in B implies A closure is contained in B. Now what is that we are assuming? We are assuming B closure is true. Now you see that B closure is closed. Okay? And we have assumed that B closure is also compact. So by our assumption, B has a compactness. By our assumption, B closure is it is therefore A closure is now a closed subset of B closure and hence compact. So A closure is a closed subset of B closure. B closure is compact. Therefore, to see that by the theorem that we have proved, A closure is also compact. Okay, what does it mean? Implies A has a compact okay, so that's a corollary which is useful. Sometimes, quite often, you'll have to use this result in this form. Another theorem is suppose Hausdorff A is contained, K is compact, and P is an element of K complex. So we are assuming X is a Hausdorff space. That is the separation properties attributed to X. K is a subset of X. K is a compact subset of X. And P is an element of K complement. Then where X is open sets, U and V, U and W such that P is contained in belong to U and K is contained in W and U intersection K is, that means you can find two open sets U and W such that P is contained in U or P is an element of U and K is contained in W and such that U intersection K is. So the situation is something. So if this is K, X, P is an element here. What you can do is you can enclose this inside an open set W and this an open set, so that intersection of W with U is 0. So how do we fabricate these subsets? That's the question that we want. How does this Hausdorff property come into? Well, let us consider the scenario. It's quite easy to, because what one does is this. You have X here, K is compact, that's what we are assuming. Then P is some element in K complement. It's an arbitrary element in K complement. Then what can we say? You choose an arbitrary element Q here. Q belonging, what you can say? Because it's a Hausdorff space, you will see that you can separate P and Q using, say, U containing or U alpha containing P and V alpha containing, or we will put it this way, UQ containing and PQ containing Q and UQ containing P, both open such that UQ intersection P is L. So we have chosen an arbitrary point in X which is not in K, and then choose for any point Q. You can find open sets VQ and UQ. Okay, VQ contains Q, UQ contains P, or has P as an element, and you see that the intersection of these two. Now this you can do for every Q. Therefore, what you get? So we have obviously the collection VQ, Q belonging to K, is an open cover then there exists VQ1, VQK, or there exists points Q1, Q2, Qk. Okay, in K such that PQ1 such that K is contained in VQ1 union VQ2 that means there is a finite subcover which does the covering. Choose this. Now you look at consider UQI, the sets UQI now you see that you take the intersection. So you take UQ1 intersection UQK is open and contains P. And P belongs to UQI okay, which implies P belongs to let's choose U as intersection UQI I running from 1 to K. Then U is open and P belongs to U and U intersection see U intersection V is empty where V equal to V21 okay. So you see that there exists an open set and of course clearly K is contained in V and the intersection U intersection is empty and U contains okay. So we have actually literally constructed sets U and V with this required. So that's a very nice result which is useful further. Now let us look at some of the corollaries. The first one, compact of compact subsets of Hausdorff spaces are. So let us prove this. This is a consequence of this. It's a very nice result that all compact subsets of Hausdorff spaces are. Let us work out the strategy. So let us start with the notations. Assume it's a compact subset of and X is what we claim is K is closed. Now how do we prove this? K contains all its limit points. That's what we prove. So that K is closed. So we take any point. So how we prove this is we show that no point in K complement is a limit point of how do we prove this? Or let P belong to complement. Claim true P is interior point of complement. That is where exists there exists an open set containing P that such that U intersection that's what we want to do. U intersection K is empty. So let us prove this. So now you see that P for any Q, P and Q are biochemical. Therefore, there exists BQ containing Q and UQ containing P such that PQ is open, UQ is open and VQ now this is what is the separation property? Is the Hausdorff property is used there. Okay. Now clearly K is contained in union Q belonging to K. So this is an open cover. So VQ for K. What does this mean? This implies since K is compact, there exists a finite subcover for K Qi belongs to such that now you take UQ1, UQ2, etc. Is open and contains and P belongs to, because P belongs to each one of these. Okay, so clearly okay, now K is contained in V, which implies that U intersection K is, that is P cannot be, this P is an interior point of K complement. That is, every point in K complement is an interior point of K complement. So it cannot be a limit point of K. So every every compact if K is a compact subset of X, where X is a Hausdorff space, then K is okay. The second column. If F is closed and K is compact in a Hausdorff space, now give a proof of this proof is it. So K is compact which implies K is closed. This is what we have proved. Now K intersection F because we are assuming F is closed. So K is closed, F is closed, therefore K intersection F is closed. Okay. So K intersection F K is compact, K intersection F is closed. Okay. So therefore K intersection F is a closed subset of K. And K being compact, from what we have proved just now. Because K intersection F is a closed subset of K, therefore compact. Now I think I'll stop today's lecture here, and then we will continue with more properties of which are the consequences of compactness and Hausdorff's separation. Thank you very much.